In this tutorial, we will see how much are the heat losses from a heated apartment to the neighboring unheated or less heated apartments. We will see how increase this total consumption and total bill from the ideal situation when all neighboring apartments are heated. Have you ever entered in a cold winter day in an unheated apartment surrounded with 4 heated apartments in a thermic isolated block of apartments? You will be very surprised that the temperature in the unheated apartment is almost similar with the temperature in a heated apartment. How is this possible? Let's see. We will analyze first 3 situations: an unheated apartment surrounded with 4 neighboring heated apartments, a heated apartment surrounded by 4 heated apartments, and a heated apartment surrounded by 4 unheated apartments. Here are the conditions for calculation. The apartment block is located at a latitude between 40 and 50 north or south. The apartment is thermally insulated to the outside. The slabs between the floors are made of concrete and are not insulated. The apartment's lateral walls are made of concrete or bricks and are not insulated. The heated apartments from those calculations are not at the first or at the last level of the apartment block. 20 degrees is standard internal temperature for apartments. For this temperature are made calculations for energy performance certificate, and 80 degrees after calculation, it's a medium internal temperature for an unheated apartment with all 4 neighboring apartments heated at an internal temperature of 20 degrees. So 20 degrees is for heated apartments and 80 degrees for unheated apartments. And let's see for those 3 situations what's happening with thermal flows. In the first situation, where we have an unheated apartment surrounded by 4 neighboring heated apartments, the inputs flows from neighboring heated apartments from the 20 degrees to 80 degrees, let's say, will be equal from the principle of conservation of energy with the thermal flow to exterior air. Well, exterior air for those zones, it's about 5 degrees. Another situation is our heated apartment at 20 degrees surrounded by 4 neighboring also heated apartments at the same temperature. So the flows internally between apartments are 0 because the temperature are identical, and the thermal flows to exterior air is from heat source, and because the temperatures are almost similar, very little difference for the easy of calculation, we'll presume that those thermal fluxes to outside are the same. Another situation, it's a heated apartment surrounded by this time by 4 unheated apartments. This time the situation is reversed with the first one, only that time the thermal flows is in the other direction, so our apartments doesn't receive but sends thermal flow to the heated apartments, also has the same as in other 2 situations, the same thermal flow to exterior. Because we established that those flows are identical, the flows to unheated and the flows to exterior are equal, and the total consumption will be double. Now let's see some calculation. I leave it here to look. If you are not interested, you can skip over them. The most important part is from calculation for different types of apartment. The internal equilibrium temperature is between 17.5 to 18.5, but for the ease of exposure, we'll consider an internal equilibrium temperature of 18 degrees. The energy transfer from the heated apartment to the neighboring unheated apartment or to the exterior air is proportional with the area on contact surface. The area total contact surface for an apartment surrounded by four neighboring apartments is this one, 2, or area upper lower plate plus 2 or all lateral walls, and the total energy lost from the heated at 20 degrees apartment to all neighboring unheated 80 degrees apartments on year is similar with the energy necessary to heat at 20 degrees apartments a year, with the apartment and all neighboring apartments heated at the same temperature of 20 degrees. This energy is for used for in calculations for energy performance certificate. Also, energy lost from the heated 20 degrees apartment to an unheated 18 degrees apartment on a specific surface, it's this formula, a proportion from area of contact with that apartment to area of total contact or for neighboring apartments, and also with this energy necessary to heat at 20 degrees apartment a year. If lateral walls are made of energy efficient bricks or autoclaved arrayed concrete, or are insulated from an area of contact between heated apartment and unheated one, the value will be the zero. Here is an example of apartment. Here is the front face for the outside, which has a length of 12 meters. Here are the lateral walls, which have 5 meters. The height is 2.5. The back wall faces to the hall have no thermal transfer, will presume the hall temperature is apartment temperature. Here is a real lateral right wall. Here is a area of lower plate, a area of upper plate similar with this one, and also the left wall area is similar with the right wall. Area of total contact between heated apartment and the four unheated apartments is the sum of those areas is 145 for this apartment. And energy lost to the left or to the right to unheated apartment on year is proportional with this divide, which is approximately 10% of energy necessary for heating one apartment at 20 degrees. Again, it's an apartment surrounded when we have those calculations for energy necessary, surrounded by all four heated also on 20 degrees apartments. Energy lost to upper lower to unheated apartment a year is for each plate, upper or lower, a percent of 40% of energy necessary for heating, again at 20 degrees. Now we will analyze three situations. Apartment heated at 20 degrees with two unheated upper and lower. Another situation heated at 20 degrees with lower and lateral. And another 20 degrees and down 18 degrees unheated apartment. In the first situation, energy losses to the above, to this apartment, between 20 and 18 degrees, it's 40% for the energy necessary to heat this apartment. Energy losses to the below unheated apartments is 40%. So totally losses are about 80%. Energy losses to the left unheated apartments are 10% because this is the area of the left wall to the all surrounding four apartments. Energy losses to the below unheated apartments is 40%, so total losses in this situation is 50%. Energy losses to the below unheated apartments, it's again 40%. Now is a situation if the lateral wall are made of energy efficient bricks or autoclaved aerated concrete or are insulated from apartment contact between heated apartment and unheated one and will take the area with value 0. So energy losses to the left will become 0. Energy losses to the below will become 50% and energy losses to total will be 50% because the total area of surrounding, let's suppose that also this wall is isolated. So only those two upper and lower area are total area for transfer. So one of them is 50%. Now let's see what's happening. So we analyze now what's happening for a transfer between an apartment of 20 degrees to an apartment on 80 degrees, 18 degrees. So this is the formula with the ratio of contact and total contact for the 2 degrees between those apartments. But because we know the transfer is proportional with the difference of temperatures, that it means that if we will have only 1 degrees, so a loss between an apartment of 20 degrees and an apartment of 90 degrees, will have divided into the older formula for 2 degrees. And after that, we can conclude that if we a general formula, if we have temperature T1 and another apartment T2, this is the formula which describe the losses from T1, which we'll suppose is superior to T2, which is inferior. And this is the energy necessary to heat the superior T1 temperature apartment a year. Now let's see those formula in application for those three situations. This is a superheated apartment at 24 degrees surrounded by normally heated apartments at 20 degrees. This is a intermediary heated apartment at 22 degrees with another surrounding 20 degrees, and this is a mixture a little bit complicated to understand the more complex and total formula. For the first situation, energy losses to all four neighboring apartments, the formula is the difference of temperature divided 2, which is 2 in total, multiply with 100% because 100% is the total area for this thermal flow. That it means that this in this situation, these apartments will have an energy loss of plus 200% with his uh, loss normally lost to outside another 100%, so the bill will become 3 times larger in this situation. In this situation, when we'll have only 22 degrees and the surrounding has 20 degrees, energy loss for all four neighboring apartments, the formula is 22 minus 20 divided 2, which it means 100%. And energy losses to the below apartment is 40%, which means that this apartment will pay 40% less, and the energy will come from this apartment. Also, in this situation, this apartment bill will decrease with 80% because we'll take energy from this one. Because as a principle of conservation the energy, what an apartment consumes in plus is become the minus for the other apartment. So the plus of bill for this one is the minus of bill for the other one. Now this is a more complex situation. We'll have first the energy losses between 22 degrees and unheated apartment at 18 degrees. And the formula is 22 minus 18 divided to multiply 40% because 40% is the total ratio of area for all total area of contact with all four apartments for these 22 degrees apartments, which will mean 80 degrees losses in here from 22 to 18 degrees. Energy losses to the left apartment, the formula is this one, 10% is the ratio of area between them of left wall, and the difference is 22 minus 20, and it's 10%. Now we have 1 degree, divide 22 minus 21 divided to, or again 40% of ratio of area from total area for all four intersections, which will mean 20%. And in this case, for the right, we have the same temperature and the difference of temperature is 0, so energy losses are 0. And total is 110%.